Right, so I've been running Robot Club at KES School for about the last 9 years. And about 4 years ago, in conjunction with Peter, we started using UKMARSbots. And that's all been going quite nicely. And then about a year ago, we had a new head of IT, and in discussions with them, I found that they were switching over to using Python in the classrooms for their IT classes, which then led me to think, well, I suppose we ought to see if we can do something with Python. Round about that time, may have been slightly before that, the Pico came out, and within a month, I think, of it being available in the UK, I hacked together a little converter board and stuck that in there and managed to get a Pico-based UKMARSbot running. But then thinking, as we came to this school year, about potentially using Python, I thought, well, that's just a bit too messy, complicated, and too much work for me to get all the bits working to put together. Unfortunately, at that stage, I came across the Cytron Maker Nano RP2040, which has exactly the same footprint as an Arduino Nano, virtually the same pinout. It has the advantage over the Pico. It actually has 4 analog ports rather than the 3. It makes 4 available, and they're all usable. And so from that point of view, it seemed like a good idea. So basically this year, starting in about middle of October, I think, with my new group of Year 8s, because we have a new group every year, we started using the UKMARSbot with, there we go, with the Cytron Maker Nano. So this is basically the item. We use the Adrian Edelston sensor board on the front if we want to use it as a maze solver. But we always start, in fact, with the class with line following. And again, over the last few months, basically we've managed to get some reasonable line following with a group of about 7 or 8 lads. A few of them have, in the last week, managed to get a bit of drag racing, but none of this year's lads are up to doing maze solving. But I thought before Christmas, well, I'm sure it's got to be possible with this, so let's put one together and see how it works and see what we can make it do. So basically, that's the spec. The one thing you may or may not have seen, again, is these, I got it from PyHut. They're a 30-to-1 geared motor, but with the encoder built in and with a nice little socket, so you just plug in the lead that they provide and that can wire straight into the motor pins. And that's been quite a useful thing to have on it. Okay, so software development for school, easiest thing to load on with Phony. You have to use one of the later versions of it so that it supports the Raspberry, the Pi Pico, and in the Cytron board, it thinks it's basically a Pico, so you select the same stuff there. But pretty much straightforward, and it uses MicroPython, and Rob helped me sort out a few bits in terms of just knowing the differences between different versions of MicroPython and all that sort of stuff. But that's been really easy to use at school, and because they're being taught a little bit of Python, although their skills are not very good at this point, at least it's consistent with the sort of stuff that they're doing at school. Okay, so in terms of my maze solver, which I've put together just before Christmas, I really wanted to keep it as simple as possible, so I thought, well, I won't take, you know, the core code and convert it to Python. I'll just start from scratch. I'll do the minimum of everything, and we'll see if we can get it to work. So there's no sort of 1 millisecond, 2 millisecond systic on it. We don't bother with that. If we're processing something, going down a straight or whatever, we just do it as fast as the processor can do it, and that seems fine. The motor's only ever run at 2 speeds plus stopped, either going at about a third of their nominal max speed, or at a third of that speed when they're going around a corner. And as I say, turning round corners is simply a question of slowing one motor down to a third of the speed of the other one. And then there is a very simple controller that says, is the speed in terms of the encoder pulses coming off this one 3 times as high as the other one? If not, speed up one of the motors a bit or slow it down a bit. And I only had to put that in because when the motor's running slowly, it's not quite a linear process with the PWM and the speed it actually achieves. So it's got encoders on it, and it uses the encoders to measure the distance gone. Those are the commands to set up the interrupts in there. And all the interrupts do is basically just add one to a count and then disappear as quickly as possible. So the interrupts are doing very little while they're there. One of the things, because I didn't really know what it was going to do and I made loads of mistakes anyway, I needed some reasonable debugging on it so that I could see whether I'd actually written a decent maze solver and what the maze walls were looking like, those sort of things. And so it's got a debug mode, so I can select either normal running or the next version on the buttons. When you select it, it says put it into debug mode, and at the end of every move it pauses so that you can see, oh yes, it went forward to the edge of that cell. Oh, it stopped, right, I can now see it. Oh right, now it's trying to go round the corner. It's done that bit of the thing, it stopped again. And when it stops, it also prints out on the system console, if you've got it connected, a whole load of information that's quite useful. So for instance, when I was checking this out recently, I put it in here, it's trying to get up to there. It went up there and went straight into that wall, and I couldn't see why on earth it was doing that. So using the information that comes out, and this is a direct copy of what's coming out on the log while it's connected, so I can see what are the maze walls that it's seeing, and again that's the coding structure for the maze walls. I can see that when I started it off, it does a calibration of the 2 side walls, so I've got the calibration values there. It's telling me where it's heading for in terms of the middle cell, and now it's doing the first move, and it's going to go ahead 3,000 encoder pulses, which is the sum of both encoders and all the numbers that we can get out of it, and then it's setting the walls in cell 16. So that's cell 0, that's cell 16, so it's seeing into 16. It's now setting the walls. It's then going to go on and do various other things, and I can sort of see pretty much what's going on and why in this case it didn't see that wall. And it turned out it was just a dry joint on one of the sensors, and it stopped me being able to, well, it was looking to see the wall with both the front sensors. Because one of them was failing, it only saw it with one, so it said, oh, there's no wall there, and smashed straight into it. But quick bit of soldering, and that sorted that out. But just having that available was really very helpful. Okay, so in terms of the routines, what it does, it sets up the maze and the walls and the boundaries initially. It calibrates the side walls. Unfortunately, you can't easily calibrate the front wall at that stage because you're not seeing one close by. And I probably ought to put something in that gives me a better way of calibrating it. And a good suggestion that somebody said today was do your calibration separately, write it to a file, and then read that in. And I'll be pinching that idea. So great idea, thank you very much. Okay. At the start, it just backs up to the rear wall, as I think lots of us do. And also when it turns around, it backs up to the rear wall as well. And again, it's fairly straightforward. For each cell, it reads the sensors, it sets up the walls that it can see for the cell that it's looking into. It then floods the array using a proc list array. So it puts items into the array, works through, finds the shortest route or route that it knows about. Then there's a thing that says decide where you're going to go based upon the flood information that you've got. Am I going to go straight ahead, turn right, turn left? Then it calls the routines for actually doing the turn right, turn left, or go straight ahead. And then have we reached the middle? If not, carry on doing it. If you have, turn everything round and start coming back the other way. Okay. That's about that bit. Okay. So, and again, the turning is pretty straightforward. We move forward a centimetre. We slow the inner wheel down to a third of the outer wheel. We check for the number of encoder pulses on each side and make sure that one of them is 3 times the other side and tweak it if not. Then when we've done that for a number of pulses, in fact we only track the pulses on the outer wheel, the one that's going the furthest. We then reset the inner wheel speed back to the speed of the outer one, which means we're going straight forward again. So we then go forward at that stage a centimetre, which should then take us to the cell boundary. And that should be a proper 90-degree turn. And we've had a centimetre at the beginning and at the end, where if there are any walls, it can be doing a bit of alignment on to sort of track up on as well. In terms of tracking, we don't actually track the wall, we avoid the walls. Again, it's using just a scheme that Peter's talked about previously. If you're trying to track the wall, you get the problem of at the end of a wall where there's a gap, you sort of tend to tail off. If all you're doing is making sure you're avoiding the walls, then you don't get that problem. So basically we're doing wall avoidance based upon whatever walls we can see. Okay. Flood routine, probably a pretty standard one this. It took me about half a day to write it and to get it working. It floods from the start. You tell it where you want to flood from and flood to, so it's easy to turn it round to flood back the other way. Clear it to high values, set the current cell to where you're starting and put a 0 in that. Then you have a look at basically what are the cells next to it. Check for those. If there's no wall, then potentially you can get there, so you can add 1 to the number unless it's already got a number in there, in which case you see whether it's a lower number or a higher number. And then you do that to go round for all the ones that are around the cell that you're currently looking at. You put them in a list, and then you basically process those in turn. And when you get down to the end, you know you've got your flooded. If you run out of proc list items before you've reached the finished cell, then you've got a flood failure, which basically means it can't find a flood route through. It's about 50 lines of code in Python, so not a particularly complex routine, and it seems to work fine. Okay. So it is all made of lots of little routines, and they all just, call each other. So just looking it through those fairly quick, it's pretty obvious what most of them are: backing up, beeping, waiting for a button to be pressed, calibrating it at the beginning, checking the speed. That's really just making sure that when we've applied any adjustments to the motors, we're not going negative, or we're not going above the 65,000 value that we can have. Resetting encoders, testing the encoders, flooding. Go ahead basically says go ahead a number of encoder pulses and avoid the walls as you're going along. Pretty much all straightforward photo read. There's quite a few test routines in there again, and again I can from the buttons on the mouse I can select test routines. I can do photo testing, I can do motor testing, and all sorts of other bits and pieces. I can print out the walls. I can show what's happening on them. It's about 1,000 lines of code with it's about 40 routines there. So what's that on average? 25 lines of code in each one. So again, lots of nice, small, easy, modular, easy to debug bits of code to do the various activities that we need it to do. Okay. So does it work? Right, that's a good question. Right, so this is my home test maze. It's a 6x3 on a bit of MDF. That's where I'm starting, that's my target. Right, so yeah, so we're looking first of all to see where we think it's going to go. Well, because of the way the flood routine works, it will go up until it gets level with or past the target cell. So in this case, it's going to go past the target cell. It's going to carry on up there and go across the top and then drop down. Hopefully then it will then carry on back this way. On the way back down, it will find this route back. It will come back down to here. It'll turn around again, and then it should by then know that this is the better route, and so it should come back up, this one up to that one. And so that's it going up past the target cell, turning across, coming up, down, stop, quick beep, carry on down through, turn across there, down to the start, turn itself round, back up, back off. Bit of a wiggle there, but it straightens it out and it ends up in the cell. So yes, it does work. It's fairly straightforward, fairly simple thing. And what I don't know is how it's going to work on a bigger maze, because that's the biggest maze I've got that I can try it on, but we'll find out tomorrow. So just another example here. Again, slightly different one where it has to negotiate around the top a bit more. This was a couple of days ago. I just ran this one, just making sure it was still running, basically. And it comes down and stops there. And then it comes down and said, oh, dead end. Right, so back up there. Now we've got a twiddly bit here, but it manages just about to get through there and straighten itself out enough. And at that stage, it should now find the shorter route, which is the twiddly one through the middle and to the end cell. So if anybody wants any of that code, it's available on my websites, and also the slightly modified version of this presentation that I gave at one of the online events that we ran a few months ago. So any questions? That's it. Oh, just one thing I will mention. Because when you fit the Cytron Maker, you've only got 4 analog ports. I don't have the 4-way switch. But what I do have is a button on the Cytron Maker and also 2 colored LEDs. And so I can use the LEDs on the Cytron Maker and the button to cycle through a number of different options for programs to run, and then select one of them by pressing the button on there, and away it goes. Again, the extra little thing on here is on top of the standard board. We actually put 3 pins there, and I use those to light 2 LEDs, and so as it's going along, it's telling me which walls it's seeing, which walls it thinks are not there, etc.
I've got a question about the wall avoidance. Yeah, is it proportional or just on-off?
That's a good question.
It looks like on-off on the video.
It is pretty much on-off. Yeah, it basically just says, oh, if I'm too close to a wall, just nudge it over a bit. I mean, that could simply be improved to make it probably control a bit better, but it seems to do the job at the moment. So I haven't, basically, with all the stuff that I'm doing at school, I really haven't had time to do much more on refining that. But, you know, it's a basic bit of code. And again, if you want to use any of the routines, if you want the flood routine or anything like that to look at, to compare with what you've got, then I say just help yourself to it and make the most of it. The other thing is that, again, because I'm doing all this stuff for schools, there is a whole load of stuff on my school's website as well, which is davidhannaford.com/KES2024, I think should be. And there's loads of pages of stuff there, which are sort of little routines that we give the boys to help get them going. Okay, any more questions? No? Oh,
Thank you very much.
back on schedule.